Hello dear students, welcome to the series of sessions where I am discussing few subtopics which are very relevant, very important for JEE Advanced and also for JEE Mains. In today's session, I will be talking about series expansion of functions and their simple derivation. You may be knowing it already. You must be using these expansions in the questions of limits. In fact, they can be used in few definite integration questions also where estimation is to be done. In fact, this kind of questions has been asked in JEE Advanced. I will show you in today's session itself. Now, you know how e power x is written. You know ln of 1 plus x. These expansion you must know. If you do not know, please remember it without any doubt, any confusion. You should remember e power x ln 1 plus x sin x cos x. But suppose you are having question where tan inverse x or sin inverse x or secant x is needed, then you may have to do something if you do not remember them. I will tell you the idea, and let me tell you, some of you might be thinking that it is some Maclaurin or Taylor. It is not. That is definitely a method to expand any function, but I will give you even better, even simpler, easier method than Maclaurin or Taylor's method. Please see. So dear students, I will like to talk about Daksh, who got All India rank 15 in JEE Advanced 2025. He also got full 120 marks out of 120 in maths, JEE Advanced 2025, which is a very rare feat achieved by any student across country. In fact, such marks doesn't appear, are not there by any student every year also, you can say. He was student of RM 20 to 25, where I was teaching him for 3 years. The ideas which I am discussing in these sessions actually used to be discussed in his batch. In fact, some of them were given by him also. So the motivation of these sessions is to repeat the performance what he gave this year by all of you next year. Okay, dear students, I am still occupied my students of Aramb and Eklavya who will be writing JEE Advanced this year. Okay, and I would like to talk about Eklavya. This is a QR code of Eklavya Telegram channel. Please join it. There you will get all notification, all information related to Eklavya 2026. Especially those students who will be writing JEE this year in 2026. Okay, so let me start. So this is me, Surendra Jain. I am teaching maths for last 14 years. I have been teaching students for JEE Mains, Advanced, Olympiad, CMI, ISI. Okay, so let's start this session. So as I was talking in the beginning, series expansion of functions in simple derivation. When we say series expansion, so I am talking about this kind of expansion like e power x, which everyone must know, which is 1 plus x square upon 2 factorial and so on. Okay, now this you must remember, but with the help of e power x, I will like to tell you Maclaurin series and Taylor series, which I was talking in the beginning, although I will be talking about some other methods also. So what is Maclaurin series? Maclaurin theorem or Maclaurin series, you can get the detailed notes in the description link, so please go through it. So I have written very neatly each and everything whatever I am teaching here. So Maclaurin theorem I am talking about here. Maclaurin theorem says that fx is equal to f0 plus f dash 0 into x upon 1 factorial plus f double dash 0 into x square upon 2 factorial and so on. F triple dash 0 into x cube upon 3 factorial and so on. Actually, Maclaurin thought that every function can be approximated to some polynomial function. Depending upon the complexity, depending upon the nature of that function, it may be of order 3 or 4 to make it close enough to that particular polynomial function. So to make a function very close to some polynomial, he wrote this as f0 plus f dash 0 into x upon 1 factorial and so on. If it is actually a polynomial, you can see after certain differentiation it has to have its derivative equal to 0. So at that point, that derivative, all the derivative will become 0, so it will be exactly equal to that polynomial. But if suppose it is e power x or sin x or ln x, then it will be closely related to that thing. Now you can see e power x. You know, for e power x, every derivative, whether it is first or second or third, it is all e power x. So if you take e power x as fx, f0 will always be 1 1 1 1. So you can see how easily we can get this e power x expansion using Maclaurin theorem. But it is true that it is easy, but only for e power x. For other function it may not be that easy. One more thing I would like to talk about, and that is Taylor's series. That was Maclaurin's theorem. This is Taylor's series. Taylor's he gave more general result like Maclaurin's theorem. He said that you can write fx as f of a plus f dash a into x minus a upon 1 factorial plus f double dash a into x minus a whole square upon 2 factorial plus f triple dash a into x minus a whole cube upon 3 factorial and so on. So what's the difference? You can see Maclaurin theorem says you can write your function centered about origin. You can say x minus 0 whole square, x minus 0 whole cube, etc. Whereas in case of Taylor series, you can expand it considering a as a center point. So x minus a square and so on. I think this Maclaurin theorem is a special case of Taylor series. In Taylor series, you can write about any number. Suppose your question is of limit where x is tending to 2. Then tending to 2, I think this series may not be useful, but this may be useful. If your function is becoming 0 at x is equal to 2, then writing your expansion about 2 will be more useful thing than Maclaurin theorem. So this is the first idea to have your expansion. They will work for every function. This will work for every function. This will work for every function, but they may not be that easy. They may not be that easy as we want. I have prepared a list of 11 functions. You can see 6 here: e power x, a power x, ln 1 plus x, 1 plus x power n, which is nothing but binomial expansion for natural number also and for any index also. Then sin x, then cos x, tan x, secant x, sin inverse x, tan inverse x, and 1 plus x whole power 1 upon x. This I will not ask you to remember. In fact, these last I will say 4, secant, sin inverse, tan inverse, and these you can manage to derive whenever it is needed, because these terms may not be that simple. If you can remember it, is very good, but if you feel that some idea should be there so that I can derive it, so this is what this session all about. Okay, e power x, I have already told you, you have to remember it. In fact, a power x, that was also my second one. A power x is also same as e power x. It is actually you can write it as e raised to the power ln a power x. So this becomes e power x ln a. So you just have to expand e power x into ln a to get the expansion of a power x. So that is very simple idea for a power x. Here you don't have to do any other thing. You don't have to use Maclaurin or any other thing. But if I have to find other expansions, then I may need some other ideas. So this I have listed. I have written Maclaurin theorem, Taylor series. That is the same thing which I was discussing in that slide. Now let me start with some other ideas, and I will give you these ideas through the expansion, rather proof of expansions of these functions. Now first one is ln of 1 plus x. I think some of you must be knowing it already. X minus x square upon 2 plus x cube upon 3 minus x power 4 upon 4 and so on. Now how can this be derived? Please listen carefully. I will be thinking of a differentiation of log. I think the differentiation of this is 1 upon 1 plus x. And now you can think of it as 1 upon 1 minus x, and then yeah, and then you can think of this as a sum of infinite GP whose first term is 1. Okay, common ratio is minus x, so it will be 1 minus x plus x square minus x cube and so on till infinity. And then if you integrate it, this from 0 to x, 0 to x, 1 upon 1 plus x dx. The right side integration would be x minus x square upon 2 plus x cube upon 3 minus x power 4 upon 4 minus x power 5 upon 5 and so on. This was, I think, with plus sign then and so on from 0 to x. I think we are done. We are done because the integration of this is ln 1 plus x, because I thought of 1 upon 1 plus x through differentiation only. So its integration has to be ln 1 plus x, and if you put the limit 0 to x, it will be ln 1 plus x minus ln 1, and ln 1 is 0. So this left hand side is this thing. So ln 1 plus x is equal to, is what we have got, what we actually were looking for, x up minus x square upon 2 plus x cube upon 3 and so on. Okay, that's it. So very simple. I think you just have to think of the differentiation of ln of 1 plus x and use infinite GP formula. That you must know, because that there cannot be any excuse for not knowing the sum of infinite GP. So that you must know, and then doing the integration will give you ln 1 plus x. That's it. Although this I will recommend you should remember. You don't need to derive it in the exam, but this was the idea where I'm beginning with. I will be telling you, I will be using similar idea to other functions also. Then comes sin x and cos x. I think to get sin x and cos x, the simple idea is, I think you must be knowing it already, that is e power iota x is equal to cos x plus iota sin x. And then you expand e power iota x using the formula of that first one, that is 1 plus iota x whole square upon 2 factorial plus iota x whole cube upon 3 factorial plus iota x whole power 4 upon 4 factorial and so on. That is equal to cos plus iota sine. Now you have to compare real parts and imaginary parts on both sides. You will get sin x and cos x both simultaneously. Okay. In fact, I will recommend that you should remember sin x cos x also without any confusion. You have to use it. In fact, these are the results that has been used mostly by JEE. Or rather, I will say in the questions, they are the functions for which we have to use these expansion mostly. So this you cannot afford not to remember. Okay, now coming to 10x. Now let us see how 10x can be derived. This is the expansion of 10x till 3 terms. The method I will tell you, you may find for x power 7 also. I will show you how. First of all, if you try to do it by Maclaurin, to get the term till x power 5, you will have to need f of fifth derivative 0. Now fifth derivative 0 means you have to differentiate 10x 5 times. First derivative will be secant square, but if you keep doing that way, I think it will become a big task. So it may not be that practical to use Maclaurin theorem to derive this 10x. Okay, now how 10x I will be deriving? I will be using the same thing which I did for ln 1 plus x. So I will think of the differentiation of 10x, which is secant square x. Okay, and secant square x I will write it as 1 minus cos x whole power minus cos square, sorry. I will be writing it as cos x whole power minus 2. Yeah, cos x whole power minus 2. And now we know the expansion of cos, which is 1 minus x square upon 2 factorial plus x power 4 upon 4 factorial minus and so on. And this I have to raise by minus 2. Okay, I will be writing this as 1 minus t whole power minus 2, where t is equal to x square upon 2 minus x raised to the power 4 upon 24, and I will need only till x power 4, so other terms I don't need. Okay, now I will be using binomial theorem to write the expansion of it, which I think we must know because binomial theorem for any index is there in our syllabus also. So if you expand it, it will become 1 plus 2x then plus 3t square plus 4t cube and so on. Now I'll put the value of t in 2t, 3t square and so on, and I'll try to see what terms of x square I can get. So 1 here, and for x square I think I can only expect x square from t only, because in t square it will be at least x power 4. So 2t if you do, I think it becomes 1 plus x square, 2 into this thing x square, and then I need to know x power 4 term, x power 4 term. Now this x power 4 term will come not only in t square but also in t with this minus 1 by 24. So 2 multiplied with this will give you minus 1 upon 12, and in t square it will be just 1 upon 4. Now if I am looking only expansion till x power 5, that much is needed. You don't need x power 6 term, because ultimately we are going to do the integration, and then if you write one more term x power 6, let's say, then it will give you the term of x power 7. So if you need x power 7, you may find that also, and that will be a very simple idea if you go this way. Now here, now you can integrate it, secant square x, you can integrate it, and you will be getting 10x, and integration is from 0 to x, so 10x minus 10 0, and on the right hand side the integration of 1 will be x. For x square it will be x cube upon 3, and here if you simplify it is 3 upon 12, so 3 upon 12 minus 3 minus 1, so it is 2 upon 1 upon 6 I think. Or am I doing something wrong? Let me see. Okay, that 3 I did not multiply here, so that's the mistake here. So if you count 3 also here, so it will become 3 into 3, 9 minus 1, 8 upon 12, so that will be 2 upon 3 I think. 2 upon 3, if you do the integration, so it will become 2 upon 15 x raised to the power 5. So I think we have got the expansion of 10x with the help of the simple integration. But other than integration, you needed binomial expansion, you needed expansion of cos x. So minimum thing we should know, and based on that you can derive the expansion of 10x, and similarly the others also, like secant x if you need. For secant x also the idea is same. You think of its differentiation, which is I think secant x into 10x. Secant x into 10x is the differentiation of this, and this will be equal to I can write this as sin x into cos x whole power minus 2. Okay, now we know the expansion of sine, that is x minus x cube upon 3 factorial. I am writing it 6. Now if we are looking for till 6, x power 6, maybe I will need x power 5 upon 5 factorial also. That's it for sin x. And for cos x, it will be 1 minus t whole power minus 2. Once again, the t is the same thing which I used in my previous slide. That means it should be x square upon 2 factorial minus x power 4 upon 4 factorial. Okay, and so on. Okay, now using this, and you have to write the coefficient of x square, x cube, and so on, and then do the integration. You will get the result. Okay, let me see what I am getting. I think we will be getting x here, and x cube will come with 1 minus 1 upon 6. X power 5 will be coming with 1 upon 120 minus 1 upon 6 plus 2 upon 3. I think simple calculation. I am avoiding writing it because this is nothing, there is nothing complicated in this. You just have to see where all x term can come. Okay, I think it will come with 1 multiplied with x only, whereas x cube will come when this x multiplied with x square here and x cube multiplied with 1 here. So that's our 2 terms here. Similarly, for x power 5, you will get it at 3 places when x power 5 multiplied with 1 here, x cube multiplied with x square here, and x multiplied with x power 4 here. You can see what 1 minus t power minus 2 is. So you will get all these terms. Okay, then I think we are done. So if you simplify it, it becomes x plus 5 upon 6x cube plus 61 upon 120 x power 5 and so on. Okay, now in this case there is this small difference. Please understand, the difference is that if you integrate between if you integrate between 0 to 1, the integration 0 to x, actually your secant x will be this. At x it will be x, but at 0 it will not be 0. So don't discard the lower limit always. Secant 0 is 1, and that is equal to x plus 5x cube upon 6 plus 61 upon 120 x power 5 and so on. So that's how you can see this term of 1 is coming here. Yeah, I didn't do the integration. So x square by 2 and this 5, this will become 4. Yeah, so this will become 5 into x power 4 upon 24. Yeah, same thing I'm getting here also, plus 61 into x power 6 upon 720. Yeah, that same thing we are getting here also. So secant x expansion is done. That is one. Now coming to sine inverse, once again same idea. Do the differentiation of this is 1 upon 1 minus x square power half. So that will be 1 minus x square power minus half. And if you expand it using binomial expansion, it will give you 1 plus 1 upon 2x square, and then I think it will be 3 upon 8x power 4, and then it will be 5 upon, not 15 upon 8 into 6, I think 48 if I'm not wrong. So that should be the expansion of this 1 upon 1 minus x square power minus half. Yeah, correct. And then now you can write these numbers the way they have written, like you can write it as 1 plus, this will be 1 square into x square upon 2 factorial. Here you can write it as 1 square into 3 square. For that you have to divide by 3. So 3 into 8, 24. You can write it as 4 factorial x power 4. Here you can write it as 1 square, 3 square, 5 square. Okay, so 15 you have to divide in numerator also. That will give you 720. So this becomes 6 factorial and x power 5 and so on. Now same thing, integrate with respect to x. This will give you sine inverse x, limit from 0 to x, but this time sine inverse 0 will be 0, and I think we are done. You can see x plus 1 square x cube upon 3 factorial plus 1 square 3 square upon 5 factorial into x power 5 and so on. So this sine inverse x is also done the same way as I was talking about. Actually most of the ideas are based on integration. One of them was based on e power iota x, and all other are based on integration. One more thing I will tell you, that is through taking log. Tan inverse x is equal to this thing. Now once again same thing. I think I can skip this also, because its differentiation will be 1 upon 1 plus x square, and using the infinite GP concept, using infinite GP concept, you can write it as 1 minus x square plus x power 4 minus x power 6 and so on. You just have to do the integration and you get the expansion of tan inverse x directly. You can see here only. I have written each and everything in my session notes. Please download them, which is given in the description box. Okay. Now the last one, 1 plus x power 1 upon x. Some people think that it is e when x tending to 0. That's true. If x tending to 0, it is e, but it is not equal to e. It is having some expansion, and whenever it is needed, how you have to do it, please understand. You will be writing this left hand side as e raised to the power ln of 1 plus x whole raised to the power 1 upon x, which means it will be e raised to the power 1 upon x ln of 1 plus x. So that's the idea. Then you will be using the expansion of ln, which is x minus x square upon 2 plus x cube upon 3 and so on. Now it becomes e power 1 minus x upon 2 plus x square upon 3 and so on. Now you can take e common into e power, this is minus x by 2 plus x square by 3 minus and so on. Now based on how many terms you are interested in, you have to write that many terms here also. Like if you are looking only till x square, then I think x square by 3 is sufficient. There is no need to write x cube term. So if you expand it, it will become e into 1 plus minus x by 2 plus x square by 3 minus and so on, and then the whole square into 1 upon 2 factorial of the same thing and so on. Now you can see, if you open these brackets, minus x by 2 term will come from here only, there is no x term there, so it will be e into 1 minus x by 2, and then if you are looking for x square term, so 1 by 3 will come here, and I think 1 upon 4 will come here, so 1 by 3 here and 1 by 4 here, and that 1 by 2 also there, so 1 by 8, and that is x square and so on. So this is how we got the expansion of this thing, 11 upon 24 x square. This you are definitely not supposed to remember it, but you should know that how to expand it, because in the questions whenever this kind of expression is used, you can do that question after expanding this way only, or LH rule you can use, but I will go with this expansion because differentiation is also not that simple for this particular function. Okay, so now I will come to a few questions of PYQs, and then I have brought one question also, which I will discuss the idea which I have used it here, that is integration and some differentiation, then getting the function. In fact, one more thing I was about to tell you, and that was actually, suppose you want to know the expansion of, suppose we have found 10x expansion like this. Now from 10x, if you do the integration, you can get the expansion of ln secant x also, because its integration is ln secant x. What you have to do, you just have to integrate the right hand side, will give you the expansion of ln secant x. You just have to take integration from 0 to x. So this will give you the integration, this will give you the expansion of ln secant x. So whenever you can do integration easily, in fact, if you do the integration of sine and cos, you will not get much, because you will eventually get sine cos only. So there is no point using that thing here. But in 10x, and then for secant x also, in fact, secant x integration is ln secant x plus 10x. So ln of secant x plus 10x can be expanded by doing the simple integration. Just take care of whether you are getting 0 at 0 or not. If it is not, then you have to take that constant other side also. So the concept of integration gives you these kind of expansions very easily. In fact, some of them can be done by differentiation also, but I will be saying that integration is much easier, because when you do the integration, you get one term higher then whatever you have written it here. Suppose you are writing till power 5, so when you do the integration, you are getting x power 6. But suppose you are starting with differentiation. Okay, you are starting with actually other function, that is the integration of ln secant x. Okay, in this case it will be difficult, so I should not take that example. I will take that example in 10x, because for 10x ln secant x, I think I can get the expansion of ln secant x with the help of ln 1 plus x also, although that will be difficult to do. Okay, that's why I am saying integration is much easier. But suppose you get the expansion of ln secant x some other method. So to get x power 5, you have to write the expansion of ln secant x till x power 6 term. Then only from the differentiation you will be able to get x power 5 term. I hope you are getting what I am saying. But if you are starting with the differentiation of 10x, whose integration will be done eventually, so I think I am okay if I get term till x power 4, because by doing the integration I will be getting x power 5 term. So that's the difference between differentiation or integration. In fact, all the examples which I have taken, their differentiations are better, easier to find, their expansion are easier to write, and their integration is also not difficult at all. So you can make a rule that we will always do the integration to get the desired expansion. So if you are looking for the expansion of any general function, okay, so what I have said here, you can say for that function fx, you get f dash x try to write this expansion of f dash with the help of binomial theorem or e power x or infinite GP, and then do the integration will give you the expansion of fx. So that is all I have talked about so far in this session. Now this is one very simple question. Now after doing whatever we have done so far, we have to find the alpha and betas if this limit is 1, and this is a previous 2016 question. X square into sine beta x, and in the denominator it is alpha x minus sine x. Dear all, even I am talking about expansion, but still what I will say, please listen carefully, the numerator thing should not be done in some very complicated methods like expansion or LH rule. Nothing is required. You just need to write it as x square into beta x, because if you divide by beta x in denominator, you multiply by beta x in the numerator, your sine beta x upon beta x will give you 1, and that you can definitely write as 1 in between also. There is no need to wait till end for this sine beta x upon beta x to be 1. You can write it in this step itself, because it is a finite number. Whatever limit you will obtain from here, it will be multiplied with 1. So there is no point waiting for sine beta x upon beta x to be written in the end. So what I have done, I multiplied divide by beta x. So sine beta x upon beta x is 1. Beta x came in the denominator. Now this alpha into x minus sine x. Okay, now in this case you can do this question by multiple methods. One of the method is obviously this expansion. How you will be doing it? In this case it is limit x tending to 0, beta into x cube. In denominator this will be alpha x, and the expansion of sine x is, I think, x minus x cube upon 3 factorial, and other terms are not required. Minus sine, so this is minus x, this is plus x cube upon 6. Now this limit can be finite only if your degree in denominator is equal to degree of numerator if it is 1. But here you can see there are terms of x also, which will give you limit as infinite if this is not made 0. So this has to be 0, then only your limit can come equal to 1. So from this we are getting alpha is equal to 1, and if this is cancelled, alpha is equal to 0, our limit will be equal to 6 beta. Our limit will be equal to 6 beta, which is given to us as 1, and we are looking for 6 alpha plus 6 beta. So 6 beta is 1, 6 alpha is 6. So 6 alpha plus 6 beta, answer has to be 7. Answer of this question has to be 7. One very simple question. Okay, you could have done this step, this thing with the help of LH also. You may do it yourself, but I have told you how expansion is used here. For sin x, I don't claim that you are using this expansion the way I have told you, but I am telling you the importance of expansions in the exam, in the previous year questions. Okay. Dear students, there are some things that has not been asked by JEE. It doesn't mean that we should skip all of those things. If you do not know how sine inverse x expansion is written, tan inverse x expansion is written, then I think you will not feel that confident, although there has not been any questions directly on sine inverse x expansion or tan inverse x expansion. But for JEE preparation, if you are looking for full marks in maths, I will suggest you should know these expansions. Okay, now this is a question of 2020. Now I'll show you how this question was totally based on expansions. Okay, some people say that expansion was not explicitly part of the JEE syllabus, but you can see it has been asked here. Now first part, now because we know cos x is first two terms, if I write, it is 1 minus x square upon 2 factorial, and then there is a plus sign x power 4 upon 4 factorial, and so on. So can I say the integral of a part, option A, will be greater than if I just write x into 1 minus x square upon 2 dx. Why I am saying so? Because we are leaving some terms which start with positive, x power 4 upon 4 factorial. If we are leaving some terms which are starting with positive terms, so this side actually made lesser than I1, because I1 will be equal to this thing if these terms which are starting with plus sign are also there in in this integral. Okay, and because x is between 0 to 1, so other term after x power 4, that is x power 6, will be lesser than x power 4. Then x power 8 will be with plus sign, will be bigger than x power 10. So if you make pairs of two terms after x power 4, starting with x power 4, you will see all the terms are positive, positive, positive. So this I1 will be bigger than this integral, which is from 0 to 1. Now if you do this integration for x, it will be 1, not 1 by 2 actually, because x square by 2, and minus x cube upon 2 integration will be x power 4 upon 8. So 1 upon 8. Now if you simplify it, it will be 3 upon 8. 3 upon 8. So you can see I1 is greater than or equal to 3 upon 8. So A option is correct. Simple question. Now coming to B part. In B part, you need the expansion of sin x. In this case, it is 0 to 1 x into x minus x cube upon 6, and other terms are with plus sign. So with the same logic, I am claiming this integral of B part will be greater than this thing. This is my I2. Now if you do this integration, it will be 1 upon 3 minus x power 4, so that will be upon 30. So this becomes 10 minus 1, 9, 9 upon 30, 3 upon 10, yeah, same number. So B is also correct. Okay, now coming to C part. Now in the C part, the idea was just, I think I am having this question on the second slide also. So coming to the C part, in this case you can see 0 to 1 x square into, if I write 1 only, I don't write even other term like x square upon 2 factorial, or let me write it. Okay, now let us see how the values are coming. For first term, if you look at the first term, the value is coming out to be 1 upon 3. Then there will be minus sign, and that will be giving you 1 upon 5 into 2, 10 I think, because x power 5 upon 5 are 10 only, and then plus and then minus and so on. So you can see the integral of C part, let's say I3, will be lesser than 1 upon 3. So I3 has to be lesser than 1 upon 3, because we are subtracting something from 1 upon 3. Then there will be positive term, but that will be again subtracted by some other term. So overall, if you look at, it will be less than 1 upon 3. Rather, you can understand this way, then 1 upon 10. Coming to the next term, if you combine these two, what will be the next term? If I write x power 4 upon 24, it will be 6, so 7, so it will be 1 upon 7 into 24. Now you can easily see these two terms has to be negative, because this is with negative sign, then this is with positive sign. Other terms will also be likewise can be said as negative. So this I3 has to be less than 1 upon 3, but they are saying it is greater than 1 by 2, so that is wrong. So far correct options for A and B. Now same logic, if you go with x square sin x, it will be x square into x minus x cube upon 6. Whenever you are terminating this expansion with minus and the upcoming term is with plus sign, I think you can say this will be greater than. Okay, when you are terminating at this end, when next term is minus, then you can say it is less than. Okay, so that's the logic. I hope you understand this. So this will be equal to 1 upon, because limit is from 0 to 1, 1 upon 4 minus 1 upon 36, yeah, 36. So if you take LCM 36, so it is 9 minus 1, 8, 8 upon 36, I think 2 upon 9 only. So I4 is greater than 2 upon 9. So this is also correct. So you can see this question is requiring the knowledge of the expansion. Otherwise, this may not be possible to do the question at all. Okay, one more question that is based on expansion. Now you can see here what expansion I will be needing. E power x, I think binomial expansion for any index, again binomial index for any binomial theorem for any index, and sin x and x into sin square x. Now once again, let me remind you what I did in the previous question. In the denominator, I will be writing like this, x square and here x square, and then I will remove this sine square with the help of this x square as 1. Do not wait till end to write this as 1, because it is eventually going to be 1, and whatever is the limit of the remaining function, whether it is 0 or it is infinite or it is finite, 1 multiplied with that thing will not make any difference. So there is no point waiting till end to write this as 1. So it is better that read your denominator as just x cube, It is not x into sine square x for your solving purpose. It is just x cube. That's it. Now, how to do this question then? You may use expansion, although other methods are also there. In this case, x cube I can write 1 plus x cube only. I need only term till x cube, so I will write only till x cube. So 1 plus x cube for e power x cube minus, this will be 1 minus x cube upon 3. Only one term I am writing using binomial expansion for any index, plus in this case this will be 1 minus x square upon 2 minus 1. Okay, and this thing, only this thing, actually you can see this is multiplied with sin x, and the expansion of sin x is x, only because other term will give you higher power of x, so there is no need to write them. So upon x cube, this one got cancelled here, so and this one is also getting cancelled here. So you can see if I divide by x cube in numerator and denominator, it will be 1 plus 1 upon 3 and minus 1 upon 2, yeah, minus 1 upon 2. So this becomes 1 minus 1 by 6, so that is 5 by 6. So that is my beta. If you're looking for 6 beta, I think answer will be 5 for this question, will be 5. So one simple question based on the expansion. Okay. Now this is one question I was talking about in the beginning. I will like to talk about this question because this is something where you may need the knowledge of what we have done today. Although there is one alternate method also, I will show you how you can do it alternatively. So one method is, please see that if you differentiate it, okay, you can see this cube, this power 3, this term of 3 will get cancelled. Here 5, this 5 will get cancelled, this 7 will get cancelled, and you will be having degree of each term reduced by 1. Okay, so I think I can write it as, where is my pen? Yeah, so here it will be f dash x, this will be 1, I am bringing it here, this will be equal to 2 upon 1 into x square plus 2 into 4 upon 1 into 3x power 4 plus 2 into 4 into 6 upon 1 into 3 into 5 into x power 6 and so on. Now if I divide by x on both sides, so f dash x minus 1 upon x, okay, you will be left with 2 into x plus 2 into 4 upon 1 into 3 into x cube plus 2 into 4 into 6 upon 1 into 3 into 5 into x raised to the power 5 and so on. Now please listen carefully. If you do the integration of this thing, okay, if you do the integration of this thing, I think the right hand side is exactly what your function is. Just go through once again. It will be x, no, it will be actually having one extra term of x also. So what I am saying, that if we integrate this from 0 to x, that is f dash x minus 1 upon x dx, okay, then if you take x common on the right hand side, let me know if you can see it or not, x into fx. This will be x square if you take x common, so you get first term. Here it will be 2 upon 1 into 3 into x power 4. So one term of x is extra, everywhere one term of x is extra, so you are getting this thing. Now to know what is fx, I will be differentiating it and it will give you a differential equation. So this will give you f dash x minus 1 upon x. If you differentiate with respect to x, because lower limit is a constant, so that differentiation will be 0, and on the right hand side it will be fx plus f dash x. Fx, what happened? Discard. Oh, I didn't have to discard that thing, sorry. Okay. So we have reached till, you can just go through the video just few seconds back. I think we got f dash x minus 1 upon x to be equal to fx plus x into f dash x. Okay, now that has become a differential equation. Let us call f dash as dy upon dx, fx as y. So this f dash x on the left hand side, if I take common, it will be 1 minus x square. First you multiply by this x on the right hand side, and then it will be equal to x into fx plus 1. Let me check. Yeah, that's correct. So I can write this as 1 minus x square dy upon dx is equal to, or minus x into y is equal to 1. I think this is a linear differential equation. You divide by this thing, so dy upon dx minus x upon 1 minus x square into y is equal to 1 upon 1 minus x square. Okay, now in this case, yeah, it is visible. Integrating factor would be 1, actually minus plus, so it will be root over 1 minus x square. You can check. The integral of this would be 1 upon 2 ln 1 minus x square, and raise it to e will give you this as integrating factor. So my solution would be y into root over 1 minus x square is equal to, this multiplied with this will give you 1 upon root 1 minus x square dx. Okay, so here we are getting final solution y into 1 minus x square is equal to sine inverse x plus some constant, but you can see from this function at 0 it should be 0. So if you put x is equal to 0, it should be 0, so constant term will be 0. So my finally that function fx is coming out to be sine inverse x upon root over 1 minus x square. So you can see I have used the idea, that idea that I have explained you to find the series expansion. Now I think after that question is very simple. You just put x is equal to 1 upon root 2, so that will be pi by 4, that will be 1 upon root 2 the denominator, so answer will be C. Now gx is 1 root 1 minus x square, so it is just sine inverse x. So sine inverse x range will be, I think for 0 to 1 has to be d, 0 to pi by 2. Although this question can be done in one more way, I will show you how. In the next slide I have to navigate through whatever given here. So first of all, understand, in the previous session only I told you what is the reduction method. Okay, now please see. Why it is happening, I don't know. Yeah, so in the previous session only I told you this result. What is going on? Oh, okay, I got it. So I will close it and I will be, how can I insert a slide, duplicate slide? Yeah, that's good. And then this actually that was my last slide, that's why it is creating the problem. So I have a duplicate slide of this, let me see. Yeah, so I will be okay, I will use the previous slide. I think this here I am having space, so let me delete this thing from this slide and then I will use this space. Okay, just 1 minute. So here I think I can delete. Yeah, gone. Okay, so this was happening because that was the last slide. Okay, so I am talking about this question. I will be telling you another method. So what is the another method? I was talking about that result 0 to pi by 2 sine x or sine theta d theta, that is 1. Okay, if you do 0 to pi by 2 sine cube theta d theta, using that result it is 3 to 1. Okay, if you take 0 to pi by 2 sine raised to the power 5 theta d theta, it is 4 upon 5 into 2 upon 3 into 1. Okay, so now you can see, now you can look at your question once again. 2 upon 3, 2 into 4 upon 3 into 5. So in this question you can see these numbers are actually those only. Can I say this is integration 0 to pi by 2 sine cube theta d theta. This is integration of sine power 5 theta d theta. This is the integration of sine power 7 theta d theta, and that is integration of 7 sine theta d theta. Okay, so if you understand this thing, so my question here is fx is equal to x into sine theta d theta, because I am doing the integration with respect to theta. I can consider x as a constant, plus 0 to pi by 2 x cube sine cube theta d theta, that is the second term, plus 0 to pi by 2 x raised to the power 5 into sine raised to the power 5 theta d theta, and so on. Next term will be of 7 also, and so on. Now you can see I can bring each and everything in the single integration sign. Okay, because limit is same. Now inside single integration sign, it is just the sum of infinite GP, which I can write it as x into sine theta upon 1 minus x square sine square theta d theta. Okay, now we have to do this integration and we will be getting same fx. Please see how. 0 to pi by 2, I will write sine square as 1 minus cos square, so it will become x square cos square theta minus rather 1 plus 1 minus x square. Please see if it is correct. Yeah, it is correct. And then x sine theta d theta, 1 minus cos square, so x square cos square and 1 minus x square, that is correct. Now we will be putting, we can put x cos theta as t, or maybe cos theta as t. Let's put x cos theta as t. Okay, if that is so, or let me put cos theta as t. Okay, so if cos theta is t, so 0 will become 0 will become 1, pi by 2 will become 0, and that will be minus x dt upon x square t square plus 1 minus x square. What I have done, I have put cos theta as t. So the lower limit 0 will be 1, upper limit will be 0, and this minus sign will make them as 0, 1 only. Now you can do the integration directly, that tan inverse thing, I think it will be 1 upon root over 1 minus x square into tan inverse x t upon root over 1 minus x square. Integration of 1 upon x square plus a square form. So 1 upon a will come here, tan inverse x upon a, because x is multiplied with t, so 1 upon x will come, but there is one x in the numerator, that will cancel. So this is the final integration, and this is from 0 to 1. Okay, now if we put 1 for 0, as you put t is equal to 0, this will be 0. If you put it as 1, it will be 1 minus 1 upon 1 root over 1 minus x square into tan inverse, yeah, x upon root over 1 minus x square. So this becomes equal to 1 upon root over 1 minus x square into sine inverse x. You just convert tan inverse in terms of sine inverse. So you can see this way also we are getting the same expression for that fx. This question I got first time in 2020. through one of my student, okay, and I did this question this way, which you can see it here, by making differential equation, first by doing differentiation, then creating once again the same fx. So this is how I did it, and later on through some other student I came to know this question was actually meant to be done using that 0 to pi by 2 sine theta integral, and that is also a good method. I think you understand it. So this is all for today. I think this was a little small session as compared to others, but I have kept it to expansions only. The idea here was to tell you that integration, differentiation can give you many identities, including expansions. Here the idea was to get the expansion, first differentiate it, try to get the expansion of the derivative with the help of binomial or infinite GP or e power x, and then integrate it to get your final expansion. The same idea can also be used in questions like this. Okay, so that's all for today. Thank you so much. Bye everyone, take care.